In cases like the firework, where the masses of parts of the system change with time, we can't use Newton's second law directly. In these cases, analyzing the momentum of parts of the system at various times is the way to go. A great case study for this type of scenario is the rocket. Rockets are propelled upwards or sideways by ejecting mass, fuel, out their rear at great speeds. The upwards force on the rocket is due to the downward force on the ejected fuel. The total mass of the rocket fuel system is constant the whole time, but the mass of the rocket itself decreases as it propels upward or sideways. So consider this rocket, which is already out in space, with mass m and speed v. There are no external forces acting on it. It's an isolated system, and momentum is thereby conserved. The rocket's momentum at time t1 is p1 m v1. Right, that's at time t1. A short interval of time dt passes, and the mass of the rocket changes by an amount dm, which is a negative quantity. It's dm. The mass of the rocket is changing. It's a negative quantity because the mass of the rocket is going down. If the quantity dm is negative, then the quantity of fuel ejected is minus dm. Because this makes that quantity positive. This fuel is ejected at the exhaust speed, v exhaust, which is this the speed of the material relative to the rocket. It's ejected in the opposite direction from the rocket, so v exhaust is negative. The velocity of the burned fuel relative to our coordinate system is, and not the rocket's, is then, so v fuel is equal to v, the velocity of the rocket, plus negative v exhaust, which is equal to v minus v exhaust. This is the case because fuel is ejected backwards from the rocket, but it's still traveling very fast from a stationary perspective. So if the rocket's going really fast, yes, the fuel is going backwards relative to the rocket, but it's still going forwards very fast, or at some speed, relative to a stationary point of view. The momentum of the ejected mass being minus dm, right, is v fuel is equal to negative dm v minus v exhaust. At the end of this interval dt, the velocity of the rocket has increased to v plus dv. And its mass has decreased to m plus dm. And remember, dm itself is negative. So, the rocket's momentum at the end of this interval is then m plus dm times v plus dv. It's mv, but you are adding what changed during that little interval dt. And the total momentum of the rocket ejected mass system, which we'll call P2, is then P2 is m plus dm times v plus dv plus that of the exhaust, minus dm times v minus v exhaust. So that's including all particles in our system. Since momentum is conserved, P1 is equal to P2. Momentum before this interval is equal to the momentum after. And we can set the two equal to each other. So P1 was just mv, right? Because no fuel had been ejected at P1. And so P1 can be set equal to P2. So that means mv can be set equal to this quantity, m plus dm, v plus dv, plus minus dm, v minus v exhaust. And so if we work some of this out, and we get mv is equal to mv plus m dv plus v dm plus dm dv plus, well, minus v dm plus v exhaust dm. And so, what cancels? VDM, VDM. dm dv is a very small quantity, so we can drop that term as well. And these exist on both sides, so those go away. So a lot of stuff cancels here. And all that we're left with is m dv set equal to minus v exhaust dm. So let's divide both sides by dt. Right? And what do we get? Well, m dv dt is equal to minus v exhaust dm dt. What's dv dt? That's ma. So that means that there's a force on the left side. ma equals the exhaust velocity times the rate of change of mass over time. This force on the left is thrust. And remember, dm is a negative quantity, so that the thrust on the rocket is positive, right? So the negative dm will cancel out with the negative there, so there's positive thrust. And it's proportional to the exhaust velocity and the rate of ejection of fuel. The more fuel a rocket can eject, and the faster it can eject it, the more thrust it will have. Notice that none of this has anything to do with the ground or the launch pad. Rockets do not push against the ground to fly upwards. In fact, they work most efficiently in the vacuum of space. It's all about momentum. So I went out and bought a rocket from Flagstaff Hobbies, and in the next video you can watch me launch it out at Cinder Hills, and you can think about how the ejected mass contributes to the thrust. That's it for this lecture.